So this video will go over section 7.5 on the ideal gas law. So all four properties of gases, which is pressure, volume, number of moles, and temperature, can be combined into a single equation called the ideal gas law. And the formula is P times V equals N times R times T. So you recognize pressure times volume, and on the right side, the number of moles times R times the temperature. And so this ideal gas law is summarizing all the other gas laws that exist. They all come from that gas law. And it is called the ideal gas law because it is working well when the gas is in ideal conditions, which are low pressure and low temperature. So we don't want, this would not work with very high temperatures or high pressures. And so what is R? R is the universal gas constant. So it's a constant that has been calculated and that makes the ideal gas law work. And because there are so many different units of pressure, it has been calculated to work for different pressures. But we will mainly use those two. The R value for atmosphere when pressure is in atmosphere, and it's equal to 0.0821, and the unit of R is liter times atmosphere over per mole and per Kelvin. And if your pressure is in millimeters of mercury, then you want to use the R value that is 62.4 with the unit of liters times millimeters of mercury per mole and per Kelvin. So understand that the formula here is P times V equals nRT. R is just a constant, and you have two different values possible to use depending on the unit of the pressure. And so the R value has a complex unit, as you can see, liters times the unit of the pressure per volume, per mole and per Kelvin. And so because of the R, the unit of R, we will have to have the volume in liters, the number of moles in moles, and the temperature in Kelvin. So these units are set. They should always be, liters for volume, Kelvin for temperature, and moles for the number of moles. It's only pressure that is allowed to be either atmosphere or millimeters of mercury. So let's use this ideal gas law and see how we use it. So we'll go through an example here that is using D-nitrogen oxide, N2O, which is also called the laughing gas, is an anesthetic used in dentistry. And so the question is asking, what is the pressure in atmosphere of 0.350 moles of N2O at 22 degrees Celsius in a 5.00 liter container? So that's your text. And in that text, there is many variables that are given. Hopefully you recognize that the first number here, 0.350 moles is N, your number of moles. 22 degrees Celsius is your temperature in degrees Celsius. So if we want to use the ideal gas law, we will need to change that to kelvins. And then the 5.00 liter is the volume in units of liters. So let's move to this slide that summarizes what is given. We have the volume, 5.00 liters, the number of moles, and the temperature. But the temperature was given in degrees Celsius, so we need to change it to Kelvin. And remember that when you have temperatures in degrees Celsius, to change them into Kelvin, you add 273. So 22 degrees Celsius plus 273 is 295 Kelvin. So that's the temperature now in Kelvin. So all these variables are set. The question was asking what is the pressure in atmosphere of N2O with those variables. So what is the pressure in atmosphere? So we need to find P. And so the ideal gas law is saying P times V equals nRT. So we need to isolate P or solve for P. And so the way to do this is to divide both sides of the ideal gas law by the volume. If you divide both sides by the volumes will cancel on the left side, and it will be dividing by the volume on the right side. So then P now pressure is by itself on the left, and it's equal to nRT over volume. So all our variables are ready to be plugged into the formula because temperature is in Kelvin, number of moles is in moles, and the volume in liters. And the question is asking for the pressure in atmosphere. So that means you want to use the R value that has the atmosphere in its units. So we will use the R value that is 0.0821 liters per mole and per Kelvin times atmosphere. So now we are ready to substitute the value into the formula. So P equals, so you substitute N by 0.350 moles, multiplied by R. R is 0.0821, and the unit of R is liter times atmosphere per mole and per Kelvin. Then you multiply by the temperature, and here it's 295 Kelvin over the volume. And so V is 5.00 liters. And so you can see that this is correctly set up if you are able to cancel all units except for the one that is, that is wanted. So here moles are cancelled because we have the number of moles, and in the R, the unit of R, it's per mole. So they cancel. One is in the numerator, the other is in the denominator. Liters cancel. One is in the numerator in the unit of R, and the volume as the liters in the denominator otherwise. And we can cancel kelvins because temperature is in the numerator and the unit of R was saying per Kelvin. So they cancel. And we see that the only unit that is left is atmosphere in the numerator. So that's correct. Next, you do in the calculator 0.350 times 0.0821 times 295 divided by 5.00. The calculator answer is 1.695, etc. Here we need to pay attention to significant figures. So there is 3 significant figures in the temperature, 3 significant figures in the R value, 3 Sig Figs in the number of moles, because the 3, 5, and the last 0 to the right are significant. And then the 5.00, that's also 3 Sig Figs. So we keep 3 Sig Figs at the end. So we keep the 1.69. What comes after the 9 is a 5. So we need to round up the 69 into 70. And you write the 7 and the 0 to show 3 Sig Figs. And the unit is atmosphere. So that's the pressure for the nitrogen oxide gas. So let's go through a learning check. So the problem says, how many moles of gas are contained in the typical human breath that takes in 0.50 liters of air at 1.0 atmosphere pressure and 37 degrees Celsius? So we have a volume, because the 0.50 liters, it's a unit of volume. So we have a volume of 0.50 liters. The 1 atmosphere pressure, that's P, is equal to 1.0 atmosphere. And then 37 degrees Celsius, that's your temperature. You need to automatically remember to change the degree Celsius into kelvins. And for this, you need to add 273 to the degree Celsius to get the kelvins. And that's 310 Kelvin when you have 37 degrees Celsius. So we have the volume, the pressure, and the temperature. What is the question asking? How many moles of gas are contained in a typical human breath? And so we need the number of moles. So we need N, the number of moles. So we will use the ideal gas law that says P times V equals nRT. And we will need to rearrange the equation such that we solve for N. So to solve for N, you want to divide both sides of the ideal gas law by RT. If you divide both sides of the ideal gas law with RT, you get N by itself on the right, and it's going to be equal to P times V over RT. And we will use the R value that is 0.0821 atmosphere times liter per mole and per Kelvin, because we have a pressure in atmosphere. So we need to adapt the R value to the pressure of atmosphere. Next, we are ready to substitute the value into the formula. And so N will be equal to P times V over RT. So P is 1 atmosphere, 1.0 atmosphere on the numerator, times the volume is 0.50 liters, over the R value is 0.0821 liters times atmosphere per mole and per Kelvin, and times the temperature, temperature is 310 Kelvin. So let's cancel units. So first, atmosphere, we have atmosphere in the numerator and atmosphere in the denominator, they cancel. Liters, we have liters in the numerator and denominator, they cancel. In the denominator here, we have Kelvin and then per Kelvin in the unit of R. So Kelvin and per Kelvin, they cancel. It's a fraction of Kelvin over Kelvin, so they cancel. And we are left with mole, and mole is in the denominator of the denominator, which is the same place as being in the numerator. So that's correct. We will get a number of moles and the unit will be moles. So in the calculator, you do 1.0 times 0.50 divided by 0.0821 divided again by 310. Another way to do this is 1 times 0.50, divide, open the parentheses, 0.0821 times 310, close the parentheses, right? You want to tell your calculator that you want to multiply the two denominator together before you divide by their product. And that would give you the same answer. And the calculator answer is 0.019645, etc. So here we need to keep 2 Sig Figs because 1.0 has 2 Sig Figs. 0.50 liters has 2 sig figs. The 0 after the 5 is significant. 310 kelvins, they have 2 sig figs. And there is 3 sig figs in the R value. So the least number is 2 sig figs. So when we round this to 2 sig figs, so it's 0.019. So we keep the 1 and the 9. What comes after the 9 is a 6. So we will need to round up. And so 19 rounded up becomes 20, right? And so that's why it's 0.020. You need the 0, the 20, to show 2 sig figs, right? The 0 to the right of the 2 is significant. And that's moles. So let's practice some more with another learning check here. How many moles of gas are in a basketball with a pressure of 24.2 psi and a volume of 3.2 liters at 25 degrees Celsius? So you want to gather all the given information. Here we have a pressure of 24.2 psi, so that's going to be our P. We have a volume of 3.2 liters and a temperature of 25 degrees Celsius. So V is 3.2 liters, P is 24.2 psi, and T is 25 degrees Celsius. And you should always change your temperatures to Kelvin because when you are using temperature in equation, it should always be in Kelvin. So we add 273 to the degree Celsius and we get 298 kelvins. Sorry. We need how many moles of gas are in this basketball? So the question is asking for how many moles. So we want N and the number of moles again. So we will use the ideal gas law that relates P, V, N, and T. And again, we are looking for N. So we solve for N by dividing both sides of the ideal gas law by RT. And so we get again N equals P times V divided by RT. So we need to choose the value of R. And here you could choose millimeters of mercury or atmosphere, because the pressure here is given in PSI, and PSI is, you don't have a R value for PSI. So you will have to change your PSI to either millimeters of mercury or atmosphere. And in my slides here, I've chosen to do it with the atmosphere. So then I will change my pressure into atmosphere by using the fact that 1 atmosphere is 14.7 PSI. And that means I will use the R value that has the atmosphere in its unit. So let's change the pressure first, because it has to be in atmosphere now. So the given pressure is 24.2 PSI. That's your given amount, times the conversion factor coming from 1 atmosphere equals 14.7 PSI. So you want to cancel the PSI that are your given amount here. So you will put the 14.7 PSI in the denominator and the 1 atmosphere in the numerator. This way PSI cancel and you're left with atmosphere. So in the calculator you do 24.2 divided by 14.7. The answer is 1.6462, etc. So this is an intermediate answer. It's not asked for. So you do not want to round it. However, you want to underline where you would stop if you were to round it. to know how many sig figs you will get from this value. And here, the given amount has 3 sig figs. The 1 atmosphere is exact, and the 14.7 psi has also 3 sig figs. So you want to underline the fact that you would keep 3 sig figs if you were to round. So we keep the 1, the 6, and then you underline the 4 to show that you would stop there. However, in the next calculation, you want to use more digits, more decimals. You do not want to round because this can change the final answer if you round the intermediate answers. So now we are ready to calculate the number of moles by plugging in the values into n equal P times V over RT. So pressure is 1.6462 atmosphere, what we calculated just above. Volume is 3.2 liters over the R value in atmosphere, so 0.0821 atmosphere times liter per mole and per Kelvin. And the temperature is 298 Kelvin. So you check that you can cancel all unit except for the mole because that's what you're looking for. So we see here atmosphere are in the numerator and denominator, they cancel. Liters are in the numerator and denominator, they cancel. And then kelvins, there is the temperature in Kelvin, and the unit of R is per Kelvin, so they cancel. And mole is in the denominator of the denominator, so this is the same as being in the numerator. And so the unit will be moles. So in the calculator, you do 1.6462 times 3.2 divided by 0.0821 and divided again, because I didn't put the parentheses, divided again by 298 equals. You could also do, you know, the pressure times the volume divided by, open the parentheses, 0.0821, the R value, times 298, temperature, close the parentheses, equal, and you would get the same answer. The calculator answer is 0.2153, etc. So we need to pay attention to sig figs. Pressure has 3 sig figs coming from the PSI here. Volume, only 2 sig figs, 3 and 2. The R value has 3 sig figs, the temperature has 3 sig figs. So volume with 2 sig figs is limiting the amount of sig figs to 2. So that's why we will run to 2 sig figs. And so we keep the 0.21, but what comes after the 1 is a 5. So you need to round up. And the 1 will become a 2. So it's 0.22 moles.